NumPy is without doubt the single most useful and most powerful library in Python when it comes to data science and machine learning. In this course, we'll cover key concepts of NumPy's library's data structure called ND-array, which stands for n-dimensional array. One of the key features of this library and the ND-array data structure is performance. You will learn operations on both one-dimensional arrays and multidimensional arrays, and will also demonstrate a whole bunch of common array manipulations. By the end of this course, you'll have a deep understanding of the foundations of NumPy, so you'll feel confident and ready to apply them in your own projects. Before starting this course, let's explore what skills and knowledge you will need. In order to truly be successful in this course, it would be helpful to have a bit of familiarity with mathematics, but no prior experience is required. Basic Python programming knowledge will definitely help, though it's not strictly necessary. Our focus will be on the latest versions of Python 3. I would encourage you to set up Google Chrome as your default browser because it works best with Jupyter Notebook. You will also want to make sure that you have done Anaconda install. So, what is Anaconda? Anaconda is a distribution of Python that includes many libraries. I'm going to walk you through some key aspects of Anaconda install, but first, make sure you have the exercise files in place on your computer. Unzip them and you'll find them in your Downloads folder with actual notebooks I've prepared. We're going to download Anaconda. So go ahead and go to anaconda.com or just go ahead and Google search Anaconda download. You're going to choose Products, and under Products section choose Individual Distribution and click on Download button. Once download is completed, run the install. After installation, go ahead and open Anaconda Navigator. Now you see it comes with several development environments included: Jupyter Lab, Jupyter Notebook, Qt Console, Spider, VS Code, and others. We are going to use the Jupyter Notebook, so let's click on the Launch button. And there you have it. You see Jupyter Notebook automatically opened in your default browser. Convenient thing is that you don't need to be connected to the internet to use Jupyter Notebook. It makes use of your browser as a graphical interface window. In case you have never worked with Jupyter Notebooks before, then you can go check out the Jupyter Notebooks video in Python Programming Efficiently. And that's about it. So, let's get ready to jump into NumPy in depth. In the late 90s, Python became popular among programmers who mainly worked with vectors and matrices and therefore needed faster vector operations. The drawback of Python is that it's not initially designed for numerical computing. NumPy proved to be a perfect fit for these kinds of situations since it allows users to have their computations completed efficiently. NumPy is the most important package for scientific computing in Python and is the base for many other packages. Even though Python lists are easy to create and manipulate, they don't support vectorized operations. Python doesn't have fixed type elements in lists, and for example, for loops are not very efficient because at every iteration, data types need to be checked. In NumPy arrays, this situation doesn't occur as the data type is fixed and it also supports vectorized operations. NumPy code is cleaner than Python code, while it accomplishes the same tasks. There are fewer loops required because operations work directly on arrays and matrices. The advanced mathematical functions make life easier as well. Many popular machine learning and computational packages use some of the NumPy's features, and the most important thing is that they use NumPy's arrays heavily in their methods, which makes NumPy an essential library for scientific projects. As you can see in the figure, some well-known libraries use NumPy's features. Lastly, since NumPy is open source, you get all related advantages. It's free, so you don't have to worry about licenses every time somebody joins your team or you need a software upgrade. The source code is available for everyone. Lists and arrays are both used to store data in Python, but why would you choose one over the other? You'll be surprised that such a decision can have a significant impact on performance and memory footprint. First, let's explore what do these data structures have in common. Both lists and arrays have similar syntax. Their elements are ordered, mutable, and are able to store duplicate items. They also allow indexing, slicing, and iterating. Let's see what the differences are. The first difference is that lists are built-in data structures, while arrays must be imported. To use arrays in Python, you have to import them from the NumPy package or from the array module. Unlike arrays, which can hold only data of the same data type, for example, only integers or only strings, lists can hold elements of different types. For NumPy arrays, once we define the dimension of an array, we are limited and cannot expand it anymore. While for lists, we are flexible as it expands as we add new elements. At first glance, it seems that lists provide more benefits than arrays. However, arrays come with the significant advantages. First, NumPy arrays consume less memory. Arrays can store data very compactly and are more efficient for storing large amounts of data. For example, imagine we create a Python list and a NumPy array with 1000 elements. If we compare the size of them, you will be surprised to find that NumPy array consumes 6 times less memory than a list. While NumPy elements only need memory to store element values, for example 4 bytes for integer value, lists have to store much more information such as object value, object type, reference count, and the size of that integer value. The second benefit, arrays are faster compared to the Python lists. For example, if we want to multiply each element of a list by a number, then we should use a for loop. With a NumPy array, we can simply multiply the whole array using the multiplication operation, and it will take care to multiply each element. When we compare the amount of time this operation takes for 10,000 integers, the Python list and for loop takes an average of 1 millisecond, while the NumPy array completes the same operation in 100 of milliseconds, making it 100 times faster than lists. The third benefit, arrays are convenient to use. As we have seen in previous example, arrays are great for numerical operations because lists cannot directly handle them, making NumPy arrays an obvious choice for use in data analytics and data science. Let's explore Jupyter Notebooks and learn how to effectively use them. Now that we have Jupyter Notebook running, let's create our first Jupyter Notebook file. Go to New, and under Notebook, choose Python Free. Notice that at the top of the page is the word Untitled. This is the title for the page and the name of your notebook. Since that isn't a very descriptive name, let's change it. Every notebook can contain 2 types of cells, a code cell and a markdown cell. A code cell can execute computer code, and the markdown cell contains commands or documentation. Let's go ahead and type Python code in the cell and run it. We'll try a basic example. Write print hello NumPy. And click above in the toolbar on Run, and it will print the message. Instead of clicking on Run, you can just press Ctrl plus Enter for Windows or Command plus Enter if you're on the Mac on to run the code. If we also want to create a new cell, then we can use Alt plus Enter for Windows or Option plus Enter for Mac. We can also use Shift plus Enter, which runs the current cell and selects below one. Let's try another example by writing a basic arithmetic expression. Let's type 2 plus 8 multiplied with 5. And we get output 42. The neat thing about Jupyter Notebook is it has an autosave feature that by default will autosave every 2 minutes, but you can also type Ctrl plus S or Command plus S if you're on Mac. Apart from a code cell, another type of cell that we'll use is a markdown cell. Go to the toolbar and instead of code, select markdown and it will convert this cell to a markdown cell. When we run it, you see it's just a basic text. Markdown is a markup language which is heavily used in creating websites, documents, books, and mostly technical documentation. If you're familiar with Markdown syntax, you already know hashtag is used for major level heading, 2 asterisks for bold, etc. If you haven't used it before, just know that Markdown is a plain text formatting syntax aimed at making writing for the internet easier. You can always check documentation under Help and then click on Markdown. A common mistake is to accidentally convert a code cell to a markdown cell and be surprised why your code isn't running. You can easily spot this because the code cell is highlighted. If you ever need help with keyboard shortcuts for Jupyter Notebooks or NumPy, you can go to Help and under drop-down select Keyboard Shortcuts or Notebook Help or NumPy reference. Array-oriented computing is the core of computational science. What makes NumPy special is the usage of multidimensional arrays called ND arrays, where ND stands for n-dimensional. I'm going to show you various array attributes that help you inspect information about an array object that you're manipulating. Let's start by importing NumPy and creating a couple of array objects. You can import the NumPy module by typing the following statement: import NumPy as NP. Every time we use NumPy functionality, we'll use the NP prefix. It's just a standard naming convention. Let's create our first array of integers. We're going to call it integers. Integer equals np.array and also print it. Because we have NP, we know that array comes from NumPy package. We can access a value at a given position by using square brackets. So, if I want to access a value of the first element in the integers array, I would type integers 0. It is important to know that unlike MATLAB and R, the indexing of NumPy arrays is zero-based, so the first element of a NumPy array is indexed by a 0, and the last element is indexed by the integer n-1, where n is the length of the array and also the dimension. I can also assign a different value. Right now, integer 0 equals 10, and I'll put in 20 by typing integer 0 equals 20. And let's check it by typing integers. And there you have it, 10 has been replaced by 20. But what if I try to assign a floating point value instead of an integer? Let's type integer 0 equals 21.5. And you see that the number is truncated, meaning the decimal point of a number is chopped off. This is because in NumPy, all the data has to be of the same type. We can check data type for ND array by typing integers.dtype. This array enforces that every value that is inside of the array is of the type int64. Int is a keyword for integer data type, and 64 is the number of bytes that represent every number. Arrays can also have many other types, such as int32, unsigned integers, floating point numbers, or complex numbers. This can be enforced by using dtype while creating an array. For example, we can change it to int8. Type in small integers equals nparray integers dtype equals int8. To see the difference in size, type in integers.n bytes and smaller integers.n bytes. As we can see, the second one takes 8 times less memory. Just keep in mind, if you're not careful with dtype assignments, you can get unwanted overflow. In case we don't define dtype and have at least one float, NumPy is smart enough to determine a suitable data type for this array. To see this in action, type in floats equals nparray, print it, and check its dtype by typing floats.dtype. You should always be mindful of which data type to choose. This can have a huge effect on memory consumption and precision, which is especially relevant in machine learning algorithms. As we have seen, the NumPy array called NDArray is the central object of the NumPy package. We have learned how to manually create a one-dimensional array. Creating two-dimensional and three-dimensional arrays is also easily done. One-dimensional array can be thought of as a vector, a two-dimensional array as a matrix, and a three-dimensional array as a tensor. Even if you need more than 3 dimensions, it's simply with NumPy built-in functions. To define a two-dimensional array, we will use the nparray function as we have already done with one-dimensional arrays. Let's import NumPy as np. To define a two-dimensional array, we will use the nparray function as we have already done with one-dimensional arrays. Let's create it by typing nums equals nparray, but this time add 2 elements. Each element is a one-dimensional list. First one will contain integers from 1 to 5 and a second one from 6 to 10. Let's see how we can access the first element in the top left corner and the last element in the bottom right corner. Because it's a two-dimensional array, we need 2 indices. That's it. To select a particular element, we'll simply put the indices into square brackets after it. The first element could be accessed with the indices 0, 0 by typing nums 0, 0, and the last element could be accessed by typing nums 1, 4 because it's located in the second row and in the fifth column. There is a useful attribute ndim that we can use to find the number of dimensions. If we type nums.ndim, we see we got 2 because we have a two-dimensional array. Let's create a three-dimensional array. As you can see, an array of two two-dimensional arrays is a three-dimensional array. How can we access an element with the value 9? We have two-dimensional arrays, so we want to access element that is in the second 2D array with the index 1. Next we see it's in the first 1D array, so the next index is 0. In that 1D array, we're looking at the third element, so the index is 2. So we'll type multi-r 1, 0, 2. The same way we created two-dimensional and three-dimensional arrays, we can also create a four-dimensional array as an array of three-dimensional arrays. You can add as many dimensions as you like, but we'll learn that multidimensional arrays can be created effortlessly with the NumPy methods. Sometimes we want to construct NumPy arrays directly from Python objects like list, tuples, or list of lists. Let's first learn how to create an ND array from a Python list. First, we need to import NumPy as NP. I'm going to create a list, first list, that contains integers from 1 to 10. Go ahead and display that list. Now, we'll call npArray and cast that list as an array and assign it in the same line. First array equals npArray first list. You can see we got a one-dimensional array back as the container for this list object. The elements of a NumPy array are usually numbers, but they can also be strings, booleans, or other objects. But what happens when we create an ND array from a list that has elements that are not of the same type? So, we'll create a list and call it second list, run the code, and then create an array from that list, second array. Now let's display our array. As we can see, the array function has automatically promoted all of the numbers to the type of the most general entry in the list, which in this case is a floating point number. We can check its type also by calling dtype, that returns the data type of the array, and we got back float64. So we have our array of floating point numbers. Let's now create ND array from a list that has elements both numbers and strings, and let's see what we'll get. We're going to call the list third list, and it will contain names and integers. Now we're going to create an array from that list and name it third array. Now let's display our array. As you can see that elements of the list are made up of strings and numbers, when we create ND array, all the elements become strings. Let's see how to create arrays from tuples. Tuples are lists that are immutable, meaning once defined, the individual elements of a tuple cannot be changed. You can easily spot a difference between a tuple and a list because a tuple is written as a sequence of numbers enclosed in round parentheses. So, let's create a tuple and call it first tuple. Now we are going to create ND array from first tuple and call it array from tuple. And check its type by calling dtype, array from tuple.dtype. Since tuple contains only integers, ND array elements are also integers. Similar to the last example, let's create an array from a list of lists. We'll call the list multidim list. Now, let's create an array and call it R from multidim list. After we run our code, we see we've created a three-dimensional array. Creating arrays using the array function would be tedious if we wanted to create large arrays. Fortunately, NumPy has a few helpful functions that can create arrays filled with values. One of these functions is a range. If you're familiar with Python, then you have used an equivalent function called range. If we pass one integer, we'll get a one-dimensional array of integers starting at 0 and up to integer we've passed as a parameter. As usual, let's import NumPy as NP. And then create our first ND array using the arrange function. What we get is an array of integers. We can also use the arrange function with a starting value other than 0 by passing two arguments. One of them defines the start value and the other defines the final value. Let's create our second ND array using arrange, starting value 100 and the final value 130. Great! Let's use arrange for our third ND array. This time we'll pass three arguments. First one defining start value, second one defining final value, and the third one defining step. Step is used as a positional argument to skip value. So, if we want our array with all even numbers from 100 to 150, it will start at 100 and at 151 and have step 2. Great! So we have created 3 arrays using the arrange function. It's going to be one of the most useful functions to quickly generate an array. What if we want to create an array of floating points that have evenly spaced decimal values? The best option is to use the linspace function. The linspace function usually accepts 3 arguments: start, the starting value of sequence; stop, the end value of sequence; and num, optional, representing number of samples to generate. Let's create our array using linspace and call it first floats r. We'll give it start value 10 and stop value 20. Since we didn't specify the number of samples, by default we will get 50 spaced samples. Even though it looks as if we have a two-dimensional array due to the way it's been printed out, you can see it's only one-dimensional because we have only one set of brackets, here on opening and closing the array. We can pass the third argument. Let's create another array and call it second floats r with the same first 2 arguments and the third argument 5. And there you have it. We've got an array with only 5 elements. It's important to distinguish the difference between arrange and linspace. Arrange will take as the third argument the step size you want to go ahead, and linspace will take the number of points you want. It's extremely useful to learn how to create ND arrays with randomly distributed data because they're used in numerical and machine learning algorithms. There are lots of ways to create arrays of random numbers. One of them is using the NumPy random library and rand function. It creates an array of a given dimensions and populates it with random floats uniformly distributed on the interval from 0 to 1. Let's create our array using the rand function and call it first rand r. We'll pass just one number 10 and get a one-dimensional array. If we want to create a two-dimensional array, we just need to pass 2 arguments where the second argument will be the number of rows. Finally, let's see another function called randint that we can use to create an array of random integers. It accepts 3 arguments. The first argument is the lowest inclusive integer, second one highest exclusive integer, and the third argument is the number of integers we want to create. We are going to call our array third rand r and pass 3 arguments 0, 100, and 20, since we want 20 elements. And then run it, and there we have our array of random integers. So we have learned simple ways to create arrays using NumPy functions. In the next video, I'm going to show you how to create arrays filled with constant values. Sometimes we want to create specific types of arrays filled with constant values. NumPy provides us with functions to achieve that easily. For example, if we want to generate arrays of all zeros, we can call zeros function. First, let's import NumPy as NP and then create our first ND array using the zeros function. We'll call our array first Z array and pass in a single integer to get a one-dimensional array. Let's pass 5 and we have an array of 5 zeros. We can also create two-dimensional ND array if we pass a tuple of dimensions we want. In this case, the first number will represent the number of rows, and the second number will represent the number of columns. So let's create our two-dimensional array and call it second Z array and pass tuple 4, 5. And there we have an array with 4 rows and 5 columns. Second useful function is ones, and you can probably guess we'll use it to create an array of pure ones. We'll use it the same way as we use the zeros function. For one-dimensional array, we'll use single integer as an argument and tuple of dimensions for two-dimensional array. Let's create our one-dimensional array filled with ones. We're going to call it first ones array and pass 6 as an argument. Great! Let's create a two-dimensional array. Let's call it second ones array and pass tuple 7, 8. And there you have it. For both of these functions, zeros and ones, we can also specify a data type. As you've seen in our examples, the default data type is floating point. So, if we want to have integers instead, we will pass data type as an argument. Let's create a third array of ones with tuple 4, 5 and integers for our data type. We'll call it third ones array and pass dtype equals int. So you see, we have integers instead of decimal numbers. Sometimes we neither want ones nor zeros, but instead some other numbers in our array. And that's when fill and full functions come into play. What is the difference between those two functions? The fill function is used to create one-dimensional arrays, and full function can be used to create both one-dimensional and two-dimensional arrays. Second difference is that fill function is used to fill an already existing ND array with similar values. So, we first have to create an empty array and then fill it with specified values. How can we achieve that? We'll use empty function that creates an array that contains uninitialized elements. Let's call that array first fill array and pass 10 as the first argument that indicates the number of elements and specify integer as data type. We will then fill the array with the value 12 using the fill function. And we got our array. We'll create a one-dimensional array using the full function. Let's call it first full array and pass arguments 5 and 10. So we get an array of 5 elements that are all tens. Next, let's create our second array using the full function. We'll pass a tuple that will represent the number of rows and columns and an integer that will represent our number. We'll call our array second full array and pass tuple 4, 5 and integer 8. Nice! So we got our two-dimensional array filled with 8s. You're now equipped with different tools for creating arrays, so you can learn how to use NumPy to perform fast numeric array computations. Knowing attributes such as dimension, data type, shape, and size is very important when you're doing computations with ND arrays. As we have learned, an array is a container with a fixed size that has elements of the same type. The shape of the array defines the number of elements in each dimension. It is represented as a tuple of non-negative integers. Let's learn how to find the shape of ND array. We'll import NumPy as NP and create 3 ND arrays and call them first R, second R, and third R. For first R, we'll use an arrange function and pass 20 as an argument to get a one-dimensional array. For second array, second R, we'll use the linspace function and pass 2 tuples 1, 2 and 10, 20 and a third argument 10 to get a two-dimensional array. Finally, for the third R, we'll use the full function and pass tuple 2, 2, 2, and 10 as the second argument to get a three-dimensional array of tens. Shape function, as its name says, gives us the number of elements in each dimension of an array. It returns a tuple that contains the number of elements in each dimension. Let's find the shape of our first R. We're going to type np.shape first R. As you see, we have a tuple 20, that has only one element and a trailing comma because the array has only one dimension and 20 elements. Now let's find the shape of a second R. And we can see we got tuple 10, 2, where our first value 10 is the number of rows and our second value 2 is the number of columns. Great! And now let's find the shape of third R. And we got 2, 2, 2. Finally, let's learn how to find the size of ND array. Size will give us the total number of elements in the array. Let's find the size of our three arrays. We'll type np size first R and get 20. For second R, we got size 20, and for third R, 8. Now that we've learned the basics of ND arrays, it's time to move to the next section and explore how to manipulate ND arrays. Let's explore functions that allow us to add, delete, and sort elements of an array. For adding elements in an array, we can use two functions, insert and append. The insert function is more useful because we can specify at which index we want to add an element. Unlike insert, append adds the value to the end of the array. First, we're going to import NumPy as NP and create array first R that contains integers 1, 2, 3, and 5. Here, we'll use the insert function that adds the element 4 at index 3 and we'll print our new array. Remember, the array indexing starts from 0. Let's see our second function, append. The values will be appended at the end of the array and a new array will be returned with the new and old values. We'll call our array second R and just pass integers from 1 to 4. And then create a new array, new second R, using append that will add 5 as the last element. Deleting an element is even easier with the delete function. Let's create array third R that contains integers from 1 to 5. And just create array del R, calling the delete function on the third R that deletes the element at index 4 from third R. Our del R now contains all integers except 5. Sorting the data is usually a necessity, and it's important to be able to do it easily. NumPy provides us with a sort function, which returns a copy of the array in which the elements are the same but ordered. Let's see how we can sort an array of integers. First, we're going to create a one-dimensional array and call it integers R using the random function. Let's print it out. Now, let's call the sort function and print out the sorted array. Now, let's sort a two-dimensional array of integers. We're going to call it integers 2dim_r. Great, and we see that in the case of sorting a two-dimensional array that contains two one-dimensional arrays, both arrays will be sorted. We can also sort arrays of other data types, for example, arrays of strings. Let's see how the sort function works on an array of strings. We're going to create our array, call it colors, and type strings with names of colors as elements. Now just print it out and call the sort function. As you can see, The items were sorted in ascending alphabetical order based on their labels from A to Z. While executing NumPy functions, you may have noticed that some functions return copy, whereas some functions return the view. The obvious difference between a copy and view is that copy is a new array and the view is a different view of the original array. Copy is physically stored at another location. View gives us a differently named reference to the same location in the memory. Before jumping in to explore the difference between copy and view on practical examples, let's see what happens when we use standard assignments. We have imported NumPy as NP, and let's create our first array students' IDs number that will contain 8 integers that represent an array of student identification numbers. We'll assign students' IDs number reg to students' ID number and print IDs of both arrays. We can see their IDs are the same. Let's update students' IDs number reg so that the second element has a new value. We'll print the values of both arrays. We see both arrays have been changed, so we can conclude that assignments don't make a copy of an array object. Any changes we make get reflected in the other array. We'll create a copy of our array by typing students' IDs numbers CP equals students' IDs numbers dot copy. Let's print our copied array and see if it's the same as the original. We can easily spot all the elements are the same. Next, let's check value equality. We can do this by using double equal operator. We obtain an array of Boolean values and all the values are true, so every corresponding element of student ID and student ID's number CP is the same. Let's find out the IDs of both arrays. Now we see that these refer to different locations in memory. We're going to change the original array by changing the first element to 1000. By printing both arrays, we can see that only the original array, student's ID's number, has changed, and there is no change in student's ID's number CP array. The copy creates a completely new array, and we say that the copy owns the data. If we make changes to the original array, it doesn't affect the copy. And if we make changes to the copy, it doesn't affect the original array. This is also called the deep copy. Great! Let's create a view to our array, students' ID's number, by typing students' ID's number v equals students' ID's number dot view. Next, we'll set the first argument of students' ID's number v to 2000 and print both arrays. We see that both arrays have been changed. The view doesn't own the data, so when we make changes to the original array, it affects the view. Also, when we make changes to the view, it affects the original array. Another way to check whether an array owns its data in view and copy is the attribute that every NumPy array has, and it's called base. It returns none if the array owns the data, else the base attribute refers to the original object. Let's try it out on our arrays. And there you have it. For the copied array, we've got printed none, and the view returned the original array, so it doesn't own the data. Reshape is one of the most useful functions you will need to use when you're dealing with multidimensional arrays. It often happens that you create a NumPy array in just one dimension, and you have to reshape it to a multidimensional array later, or vice versa. key concept is change of arrangement of the array, so the shape of the array changes while the number of elements stays the same. Let me go on and show you what I mean in our first example. We have imported NumPy as NP. Let's first create a one-dimensional array of 12 elements using a range function by typing first r equals NP arrange 1, 13 and just print it out. Let me go on and show you how to convert it to a two-dimensional array. Reshape function takes as arguments the name of our array and a tuple that represents the shape and returns a new two-dimensional view of the past array. We will type second r equals np dot reshape first r 3, 4 and let's print it out. So we have a two-dimensional array that has 3 rows and 4 columns. How would you convert first r to a two-dimensional array with 6 rows and 2 columns? Simply by passing tuple 6, 2. So we will type third r equals np.reshape first r 6, 2 and print it out. Let's see what would happen if we try to convert our one-dimensional array of 12 elements into a two-dimensional array that has a shape that is incompatible. For instance, let's say we try to convert it to a two-dimensional array of 4 rows and 4 columns. We will type fourth r equals np.reshape first r 4, 4. As you can see, we got a value error, cannot reshape array of size 12 into shape 4, 4. We got an error because we can convert the array into any shape only if the number of elements required for reshaping are equal in both shapes. Next, let me go on and show you how to convert a one-dimensional array to a three-dimensional array. We'll take our first r and convert it to an array of a shape 3 by 2 by 2. Let's type fifth r equals np.reshape first r 3 by 2 by 2 and print it out as well as dimension. And there you have it. Up till now, we've explored examples of converting one-dimensional arrays to two-dimensional arrays and three-dimensional arrays. Great thing about reshape function is that it can convert an array of any shape to some other shape. We're going to create a two-dimensional array and convert it to a one-dimensional array. Let's call our array 6r and it will be an array of 3 rows and 2 columns. In case we want to convert an n-dimensional array to a one-dimensional array, we just need to pass as arguments our array and -1. This type of conversion is called flattening. Let's create our one-dimensional array from 6r and call it 7th r flat. And when we print it out, we see we have successfully created a one-dimensional array. Apart from using the reshape function, there are two other functions that can be used for flattening. They are called flatten and ravel. Difference between them is flatten will create a copy, so any change to a new array won't change the original array. Ravel will create a view, so any changes to a new array will be reflected on the original array. Benefit of using Ravel is that it's memory efficient because it doesn't create a copy. For instance, let's say we want to flatten our sixth array using first flatten and then Ravel function. We'll create two new arrays, 8r flat and 9r flat. Now, let's just change the first element of 8r flat to 100 and the first element of 9th are flat to 200. And print them out as well as our original array. And there we have it. We've seen both functions in action. One of the biggest advantages of NumPy is manipulation of large numbers of values without the need to write inefficient Python loops. To achieve this, we have to be able to refer to elements of the arrays in many different ways. Let's learn two ways to access elements in an array: indexing and slicing. We wouldn't benefit from using multidimensional arrays if we couldn't access elements between them and update them when it's needed. This is called array indexing. To index arrays, we use square brackets. Opening bracket begins the index and closing bracket ends it. Inside the square brackets, we write which elements of the array we want NumPy to return or assign. It's called a subscript. You have already experienced indexing in the previous chapter. Let's see a couple more advanced examples on how to access elements of a multidimensional array. Let's jump into our first example and see how to access elements in two-dimensional and three-dimensional arrays. We have already imported NumPy as NP. We are going to create a two-dimensional array with 3 rows and 4 columns by using reshape and arrange and called 2dimR. So, if we want to pick up an element in the second row and the second column, we are going to type 2dimR 1, 1. When we don't specify as many indices as we have dimensions, for example, in our two-dimensional array, if we specify only a single index 2dimR1, we will get the second row, meaning all the elements of the second inner list. Great! Now let's create our three-dimensional array that will have dimensions 3 by 4 by 5, using reshape and arrange and call it 3dimR. Now, if we want to access the fourth element of the third array of the first array, we will type 3dimR 0, 2, 3. And we got printed value 13. Next, the cool thing is that in the case we have bigger arrays, we can use negative indexing to access an array from the end. For example, if we want to access the last element in our three-dimensional array, we would type 3dimR 2 minus 1 minus 1. We would like to know how to select more than one point. Sometimes we want to select an entire row or entire column or every third element of a row or column. This concept is called slicing. It will take elements from one given index to another given index. The general syntax for slicing is array start, stop, step. First value start indicates the lower bound, where we start. Second value stop indicates the end. And the third value step is optional. We will use it in the case to indicate how many elements we want to jump over. Let's create a one-dimensional array that contains integers from 0 to 9 and call it 1dimR. Next, let's slice elements from index 2 to index 6. And when we print it out, we see that the start index 2 is included and the end index 6 is excluded. It happens very often that you will have to grab only the first few elements or the last few elements, and the way to do that is by omitting start or stop indices. Let's see how to grab first 5 elements. We will type 1dimR 5. Next, we can use the minus operator to refer to an index from the end. If we want to grab the last 3 elements, we will type 1dimR minus 3. Finally, if we want to access every other element, we will omit start and stop and just use 2 as third argument for the step, so we will type 1dimR column, column 2. And there you have it. We have picked up every other element. Finally, let's see how to slice two-dimensional arrays. We're going to use already created 2DMR and cut the first two rows and first two columns. So, we can do this by typing 2DMR 1 column, comma, 1 column. If we want to select just the second row, we're going to type 2DMR 1, column. So we're indexing only the second row by specifying only rows index. For instance, if we want to select just the third column, we're going to type 2DMR column, 2. As you can see in both cases, we have dropped the dimension by 1, so we've got a one-dimensional array. Up till now, we have learned several different ways to create NumPy arrays and discovered functions to rearrange arrays. In addition to reshaping and selecting subarrays, we often have to merge arrays into bigger array or break one larger array into smaller ones. For example, sometimes we have to join separately computed or measured data series into higher dimension array. It is useful when we pre-process data and need to append or combine it multiple times. NumPy provides few functions for joining arrays: concatenate, stack, hstack, and vstack. Joining will put contents of two arrays into a single array. Let's see how we can use our first function, concatenate. We have imported NumPy as NP, and now let's create two one-dimensional arrays and call them first R and second R. First R will contain integers from 1 to 10, and second R will contain integers from 11 to 20. And let's print them out. Concatenate will take as parameter a sequence of our two arrays, and the second parameter is the axis, which is optional. We will use axis when we want to specify the axis along which the arrays will be concatenated. When it's not specified, it's taken as 0. Let's call conr our new array that we will create using concatenate. And now when we print it out, we see we have successfully joined our arrays. Great! Let's head on to our second example, this time with two-dimensional arrays. Let's create an array and call it third 2dr that contains integers from 1 to 10 in two rows, so it will have 2 rows and 5 columns. Similarly, let's create an array and call it fourth 2dr that contains integers from 11 to 20. Great! Now we'll create an array called cont2dr by using concatenate to join these two arrays along rows. So we'll put axis equals 1. Another function similar to concatenate is stack. Difference between them is that stack is done along a new axis. Let's use stack on our previously created one-dimensional array first R and second R to create a new two-dimensional array called str and print it out. Great! Next, let's explore two similar functions, hstack for horizontal stacking and vstack for vertical stacking. We'll create a new array and call it hstarray by using hstack on first R and second R. Next, let's create a new array and call it vstr by using vstack on first R and second R. You have now managed to use stack over rows and columns. Now that we have learned functions for joining arrays, let's master the functions for splitting arrays. Splitting breaks one array into multiple subarrays. It can be done using the following functions: split, array split, hsplit, and vsplit. Split function has one major drawback. It will split arrays only when the number of elements is divisible by the number of splits, so the resulting arrays needs to have the same shape. Otherwise, it will throw an error. Let's see in action in our second function, array split. As arguments, we need to pass the array we want to split and an integer that represents the number of splits. The return value is an array that contains each of the splits as an array. First, we'll create a new array and call it fifth R. It will contain integers from 1 to 12. Next, let's create a new array SPR by using array split. We'll split our array in 4 parts. And there you have it. We have splitted our array into 4 arrays. If we want to access them from the result array SPR, we'll use indices. So if we want to print a second array, we'll type print SPR1. But what happens in a situation when we want to split an array that contains a number of elements that aren't divisible by split? Array split will allow our array to be divided into a defined number of splits. It will adjust from the end accordingly. Let's divide array fifth R into 8 parts. You can see how easily we've managed to get 8 arrays. The first 4 have 2 elements and the last 4 have 1 element each. Lastly, let's see functions hsplit and vsplit in action. We're going to use them on our two-dimensional array called third 2DR. So we'll create HSR by using hsplit to split a two-dimensional array into 5 two-dimensional arrays along rows. Similarly, we'll create VSR by using vsplit to split a two-dimensional array into 2 two-dimensional arrays along columns. Once we have learned a set of tools for creating and manipulating NumPy arrays, let's move on to learn arithmetic operations. NumPy has a powerful capacity to apply operations on the whole array instead of each element individually. This is called vectorization. When used efficiently, vectorized expressions will eliminate the need for many explicit for loops. The benefits are higher performing code, less verbose code, and better maintainability. There are plenty of arithmetic operations that are supported. We'll cover some of them: addition, subtraction, multiplication, division, exponentiation, and specific functions to perform them, as well as some other useful functions. Let's start exploring arithmetic operations by doing some simple calculations with scalars and between arrays. We have imported NumPy as NP. Now, let's create our two one-dimensional arrays using an arrange function. We'll call them just A and B. A will contain integers from 1 to 10, and B will contain integers from 21 to 30. Let's add them using plus operator. Just type A plus B, and we have two arrays A and B which are added element by element. It's that simple. Great, now let's see subtraction. We just need to type B minus A. Isn't that easy? Next, let's multiply by using asterisk operator by typing A asterisk B. Nice! And now let's see division by typing B slash A. For exponentiation, we'll use double asterisk operator. Let's create a third array C. that will contain integers from 2 to 12. We'll calculate a raised to the power of c by typing a double asterisk c. We can also do operations between an array and a scalar. In this case, scalar value is applied to each element in the array. We'll use our array A and multiply it with 2. And that's it. All elements are now twice the previous value. NumPy also has functions to perform arithmetic operations. You can easily remember their names because they are the same as in math: add, subtract, multiply, and divide. Let's try them out on our arrays A and B. So type np.add AB and next np.subtract BA. To multiply A and B, we'll type np.multiply AB. And to divide, np.divide BA. Lastly, I want to introduce you to a few more useful arithmetic functions: mod, power, and square root. We will use the mod function to output the remainder of the division of two arrays. Let's see it in action by typing mod BA. Great! So we got our remainders. Power function is used for exponentiation. We have to type np.powerac. Square root function is used to calculate the square root of all elements of the array. Let's use it on array A by typing np dot square root of A. Great! So we've successfully mastered arithmetic operations and functions. Sometimes we need to apply arithmetic operations on arrays with different shapes. NumPy provides us a way to achieve this with broadcasting. In cases when arrays have unequal sizes, the arithmetic operations are defined if the smaller array can be effectively expanded to match the larger array by using simple rules. According to the NumPy documentation page, broadcasting is explained as: the term broadcasting describes how NumPy treats array with different shapes during arithmetic operations. Subject to certain constraints, the smaller array is broadcast across the larger array so that they have compatible shapes. So, how does broadcasting work and when can we apply it? There are simple rules that we can use if we want to apply arithmetic operations on two arrays. For example, what if we want to add them? Then we should first move backwards from the last dimensions of each array, then check if their dimensions are compatible. Dimensions are compatible if their axes on 1 by 1 basis either have the same length or either of them have length 1. Let's see it in our first simple example. We have already imported NumPy as NP. Let's create a two-dimensional array A and a one-dimensional array B using a range function. Now let's add A and B by typing A plus B. In this case, NumPy has added two arrays. So, it first copies B along the new vertical axis to match the shape of A and then carries out element-wise addition. What if array B has only two elements? Could we then add it to match column of A? Let's create a third array C that contains only two elements and then add A and C. As we can see, in this case, value error is thrown. Why is that so? Let's check dimensions of our arrays. Array A has dimensions 3 by 3. Array B has dimensions 3 by 1. And array C has dimensions 1 by 2. We start by comparing the last dimensions of two arrays. If we check arrays A and B, the last dimension of array A is 3 and the last dimension of array B is 3. They are compatible. Next, we compare first dimensions of A and B. First dimension of A is 3 and first dimension of B is 1, so NumPy can expand B by making two copies of it along its first axis, so these dimensions are compatible. Now, NumPy can add two arrays of the same dimensions. In the case of arrays A and C, we start by comparing last dimensions. Last dimension of A is 3, and the last dimension of C is 2, so there is no way to expand C to match A. These dimensions are not compatible. Next, let's see broadcasting in action on a three-dimensional array. We'll create a three-dimensional array D that has dimensions 2 by 3 by 4 and a one-dimensional array E that has 4 elements. Let's subtract these two arrays by typing D minus E. Great! So we see we have expanded array E by copying its single column along the first axis to match E. Well done! We have learned the important NumPy concept for performing arithmetic operations. Usually, when we are faced with a large amount of data, one of the first steps is to compute summary statistics for the data under consideration. NumPy helps us do that with a set of functions for calculating aggregates for NumPy arrays, which take an array as an input and by default return a scalar as output. These are statistics such as averages, standard deviation, functions for calculating the sum and the product of elements in an array. Let's jump into our first example and see how we can compute the sum of all values in an array. There is a simple function to achieve this called sum. First, let's import NumPy as NP and create a one-dimensional array called first_r that will contain tenths from 10 to 100. And then two two-dimensional arrays called second_r that has dimensions 3 by 3 and third_r that has dimensions 2 by 5. Let's calculate the sum for all three arrays. We just need to type first_r.sum to calculate the sum of all values in first_r, and similarly for the second and third array. What if we want to calculate the sum of each column in the second array second_r? Then we have to pass the axis as argument. In this case, axis equals 0. We can do this by typing second_r.sum, axis equals 0. For the sum of each row, we would type second_r.sum, axis equals 1. Next, let's see a function called prod. Prod function finds a product of all elements in an array. We will calculate the product for all three arrays. Just as for sum, we can calculate the product only for columns. Let's try it out on our third_r by typing third_r.prod, axis equals 0. Now, we'll use another statistics function to find the average. The average function will return the average of a given array. If we pass an axis, it will return average just for columns or just for rows. Let's calculate the average for our three arrays by typing np.average, first_r, for the first array, and similarly for the second and third array. Two extremely useful statistics functions are min and max functions to find the minimum value and maximum value of a given array. Let's find min and max for our first array. We'll just type np.min first star, np.max first star. Our last stop is to learn functions for calculating mean and standard deviation of the given input array. To get the mean for our first array, type np.min first r, and for standard deviation, type np.std first r. NumPy provides many other different aggregate functions that we won't cover and discuss here, but you can easily search and find them in a NumPy documentation. Let's learn how to find unique values and how to get unique rows and columns in one-dimensional and two-dimensional arrays. We'll also explore how to find their index position and frequency count. NumPy provides the unique function to find unique elements in an array. To get unique elements, we just need to pass the name of our array as an argument. Let's import NumPy as NP and create our first one-dimensional array and call it first R that will contain 20 elements. Keep in mind that some of them will be duplicates. We can get unique values from our first R by typing np.unique first R. Great! Let's see how to get unique elements from a two-dimensional array, which we can call second R, and it's going to have 3 by 4 dimensions, also with some elements that are duplicates. Moreover, I've already prepared an array with the same elements in the second and third row and the same elements in the second and last column. To get unique values, we'll type np.unique second R. Now, we can get unique rows by typing np.unique second R axis equals 0. And we see that our third row hasn't been printed because it's a duplicate of the first row. We can get unique columns by typing np.unique second R axis equals 1. And we see that our fourth column hasn't been printed because it's a duplicate of the second column. Lastly, let's learn how to get an index position of unique values. To get the indices of the unique elements, as an argument we need to pass return index equals true. For the first array, we'll type np.unique first R return index equals true. And we get a tuple of two arrays. First array is an array of unique elements, and the second array is the array of index position of the unique elements of first R. Sometimes we also want to know the frequency count of unique elements. In that case, we need to pass as argument return counts equals true. Let's try it out in action on our second R by typing np.unique second R return counts equals true. Great! So we see we got a tuple of two arrays where the first array is an array of unique elements and the second array is an array of frequency count of unique elements. We have learned how to change the shape of an array by using the reshape function. Now, let's explore other functions for transpose-like operations: transpose, move axis, and swap axis. Important thing at the beginning is to understand the difference between reshape and transpose. Reshape function takes the input array and formats the array into a desired shape. Transpose function changes the rows into columns and vice versa, so axes are inverted. Transpose takes two parameters. The first parameter indicates the input array, and the second parameter is axis that is optional. As a result, it returns the input array with inverted axis. Let's import NumPy as NP and create our first two-dimensional array called first 2dim_r using a range and reshape. It will have dimensions 3 by 4. Next, let's transpose our array by typing np.transpose first 2dim_r. Great! So we have transposed an array, and we can see that rows and columns have been inverted and the shape is 4 by 3. In the second example, let's create a second array and call it second 2dim_r. This time our array will have dimensions 3 by 2, and we will use the transpose function along the axis parameter. By typing np.transpose second 2dim_r 1 0. Let's explore the moveAxis function that moves the axis of an array to a new position. It takes three parameters. The first parameter indicates the input array. The second parameter is the source that represents the original positions of the axis to move, and the third parameter is the destination that represents positions for each of the original axes. As a result, it returns an array with moved axes. Let's create a three-dimensional array that will have the shape 2 by 3 by 4 and call it first 3dim_r. And use moveAxis by typing np.moveAxis first 3dim_r 0 minus 1. Now, let's explore our third function called swapAxis. SwapAxis interchanges two axes of an array. It takes three parameters: input array, axis 1, and axis 2. Let's use swapAxis on first 3dim_r by typing np.swapAxis first 3dim_r 0 2. As you can see, after applying swapAxis, numbers have been swapped between axis 0 and axis 2, so our output array has dimensions 4 by 3 by 2. Let's learn how to reverse the contents of an array along the axis. Before exploring how to use the flip function, let's learn another way to reverse a one-dimensional array using slicing. We already learned the syntax for array slicing is start, stop, step. Values for the start and stop field are optional, with default values set to 0 for start and the string length for stop. If we put step -1, it indicates starting from the end and stopping at the start to get our array reversed. Let's import NumPy as NP and create a one-dimensional array of 10 integers and call it array1dim. We're going to reverse our array by typing r1dim column -1. Great! Now, let's see our flip function in action. Flip function reverses the order of array elements along specified axis, preserving the shape of the array. It takes two parameters, input array and axis along which array is reversed. As a result, it returns a reversed array with shape preserved. For reversing the array r1dim, we will type np.flip r1dim. Great! Let's create a two-dimensional array using a range and reshape. We'll call it r2dim, and it will have a shape 3 by 3. For reversing it, we will type np.flip r2dim. If we want to reverse it from left to right, meaning we want to reverse elements row by row, we'll provide 1 for the axis parameter. For our last example, let's create a three-dimensional array called R3dim that will have shape 2 by 3 by 4. And let's reverse it over different axes. We can do this by typing np.flip r3dim1 and np.flip r3dim2. So we have successfully reversed our three-dimensional array over different axes. I hope you enjoyed the course and now have a solid foundation of NumPy. You can look for more NumPy courses coming from me in the future. You can also search our library for more data science courses to continue your journey. I want to wrap up by saying thank you. You have devoted time to learning this material with me, and I want you to know that I don't take that for granted. I really do appreciate your engagement as well as your feedback on this course.